This video is mostly for Colin, who has been gone lately, and we want to try and get you caught up on what we've been doing in class lately. We're going to talk about different kinds of functions and how you can change them around. We often will divide functions up into different families that have the same characteristics. You've already looked at some of those, like you've learned that lines basically have the same characteristics, and trig functions like sine and cosine tend to have the same characteristics. We're going to learn what some of those are in this chapter, and then find out how changing some numbers in the equation will change the graph of those functions. I don't know if you happen to have a graphing calculator at home or not. If you do, you might want to stop the video as you go through it and see if you can graph the different functions we look at. If not, at least follow along, because what's going to be important is that you know the basic shape of each of the parent functions, each of the main functions that determines a whole group. When you are graphing functions, one thing that can be useful is to make sure that you are looking at the same screen as other people. And if you hit the zoom key on your calculator, one of the options is zoom standard. It happens to be choice number 6. If you select that, what it's going to do is have the axes count to 10 in both directions, and that just is a pretty standard window that makes most functions that we'll deal with look fairly good. You probably remember graphing trig functions last year, and anytime you do want to graph a function, you always hit the y equals key on your calculator, and when you want to enter the variable x, what you do is you look for the key that says xn theta t, that's basically right below the mode key and next to the alphabet key. That'll always put x on the screen. And of course, after you've entered the entire function, you would hit the graph key at the top right to actually look at the graph and see what's going on with it. So again, today we're going to look at some basic functions that are the main source of others that are in their group. We're going to look at parent functions, and then we can figure out what their children look like. And we'll start with what's literally the easiest function there is, which is y equals x. You should know, if you think about that for a second, that we're going to end up getting a line. Because the graph is a line, we call this a linear function. In your book, they refer to it as an identity function. That's because if you give me any number for x, the answer, the y, is that exact same number. It's a very simple graph. It goes right through the origin. You'll also have points like 1, 1 and -1, -1 on it. It's a line with a slope of 1. And you should remember from back in Algebra 1 that every line has the same basic characteristics. You've got slope and y-intercept, and changing the numbers in the equation for a line moves it around, changes how steep it is, changes where it goes, but it's still just a line. So y equals x is the first of the parent functions. The second graph we're going to look at is y equals x squared. You actually did this last year, although we went through it much more quickly than some other things. But y equals x squared, the difference, of course, is we have an exponent. We have squared. This is a quadratic function, and quadratic functions always have graphs that are parabolas. If you've got x squared and 2 is your highest exponent, you're always going to get a U-shaped graph, a parabola. Now it also turns out that any function that has an even exponent, any even power function like x to the 4th or x to the 6th or x to the 100th power, those are also going to end up looking a lot like parabolas. The difference if you have bigger exponents is that it goes up much more steeply. It also flattens out down at the bottom, and you end up with what almost looks like a flat tire when you graph it, but it still is just a modification of that U shape. Just like we did at the beginning of this chapter, we're going to ask questions like what's the domain, or what's the range, or where is this increasing and decreasing? Here, it should make sense that the domain is going to be all real numbers. It's going to be negative infinity to infinity, because sooner or later, it's going to go all the way to the left and all the way to the right, and you'll cover every possible number. The range will end up being just the numbers from 0 upward. You'd write it with like bracket 0 to infinity. There's no negative numbers that we ever get for answers, so the y's just start at 0 and keep on going. On this graph, we decrease through the negative numbers, and then we increase through the positive numbers. The third of the parent functions we're going to look at is x cubed. And again, if you've got your own calculator, you might want to try to graph that. If not, just wait and we'll look at the answer. The right side of x cubed, from the origin onward, looks a lot like a parabola. The left side looks a lot like an upside down parabola, and in fact that's almost literally what's going on. It's like you take the x squared graph and you turn the negative part of it upside down. That's what ends up happening to make x cubed. That's because if you take a negative number to the third power, you get a negative answer. That's why our graph ends up being in the third quadrant over at the left-hand side. We do call this a cubic function, and it does turn out that every odd exponent, like x to the 5th or x to the 93rd, those would be the same basic shape. They start at the bottom on the left side, go up quickly, kind of flatten out in the middle by the origin, and then rise again quickly through the positive numbers. That's a cubic graph. Here's a different version of the same graph where you can actually see things a little bit more clearly. And you can tell, for instance, that the points 0, 0, 1, 1, and negative 1, negative 1 are on that graph. You can tell that beyond there, it rises and falls very quickly. This would also have a domain of negative infinity to infinity, because it will keep going at the left and right sides. And you can tell the range goes clear to the bottom, clear to the top, so that's also negative infinity to infinity. The next function we're going to look at is 1 over x. You can, of course, type that into your calculator just using the divided by key, 1 divided by x. 1 over x means the reciprocal of x, and this is called a reciprocal function. We actually learned about graphs like this at the end of the year when we were online last spring. This is what's called a hyperbola. The hyperbolas you did last spring, mostly they opened either across or up and down. This one, it kind of goes diagonal. But you can tell that there's kind of an upside down L shape in the third quadrant, and then a right side up L shape in the first quadrant. Again, here's a little bit better looking version of the same graph, and there's a couple of things you want to notice about it. One of those is that it never crosses either the x or y axis. Back when we were in advanced algebra, we called that an asymptote, where it's a line you get close to, but you never actually cross. And here it doesn't cross either of the axes. That's because if you tried to take 1 over 0, it's undefined. And if you try to put in big numbers and take 1 over a big number, you're going to get a very small fraction, but it's not actually equal to 0. If you think for a minute, that's going to actually make some exceptions when we figure out the domain and range, because this time the domain does not include 0. It's going to be negative infinity to 0 with parentheses, and then 0 to infinity. And actually the range is the exact same thing. It goes from the bottom to the top, but it skips over 0. This one, it's decreasing everywhere. It's decreasing on the negative side, and it's also decreasing on the positive side. Another way to enter 1 over x is x to the negative first power. And in fact, when you have negative odd exponents, they're going to end up having graphs that have infinite discontinuities, like what you're looking at here. Again, you're always going to have asymptotes along the x and y axis. One more variation is what happens when you do 1 over x squared. And this is going to be just a slightly different kind of graph. We call this the inverse square function, and you end up with what to me almost looks like a volcano or a trumpet that's sitting on the floor. It's kind of wide when you're along the x-axis, and then it has an asymptote going up to the top. Again, here's one where you can see it just a little bit better. I sometimes think this looks like a volcano. That's another way to think about the shape. The idea is when you plug in smaller and smaller numbers, when you square those and then flip them over, they get very, very large, and that happens on both sides. Just like before, we have asymptotes on both the axes. This one, the domain would be negative infinity to 0 and 0 to infinity. The range, the y's, are just going to be 0 to infinity. This function, it's increasing through the negative numbers and then decreasing through the positive numbers. And again, this kind of graph would happen if you did 1 over x to any even power. Next, we're going to look at the function square root of x. Y equals the square root of x, which you could actually enter as x to the 1/2 power if you wanted, but square root is the function. It's important to realize that square roots are not defined for negative numbers, because if you put in a negative, you'd get a complex number answer, and that doesn't make sense when we're graphing functions. So the domain here would have a bracket at 0 and then go to infinity. The range is also going to be 0 to infinity. It's going to keep on going up, although a lot more slowly than some others. What this actually is half of a parabola that's going sideways instead of up and down. Here's another version of the same thing. Again, you notice it starts at the origin and it keeps on going right and upward. The last two of the parent functions we're going to look at today require going a little bit deeper into your calculator if you're graphing them yourself. What you need to do is go into the math menu, and math is over at the left-hand side. At the top, it has a number of choices, one of which is number. And if you go to math and you use the right arrow key to go over to number, the very first choice that's on there is ABS, which stands for absolute value. And so next we're going to look at the graph of y equals absolute value of x. When you've encountered that before, it's always had vertical bars around the x to stand for absolute value, and some newer calculators will actually show it that way. But in the older ones, it uses a computer science abbreviation, which is ABS. When you graph absolute value, you get a V-shaped function. And that actually should make a little bit of sense if you think about it, because what you have is that if you have a negative number and you do the absolute value, the answer is positive. That's where the part on the left is coming from. If you do a positive number and you do the absolute value, you just get back what you started with. And of course, the absolute value of 0 is 0. What's actually up with this graph is on the right, you have the exact same graph as y equals x that we did at the beginning, but just on the positive side. And over on the left, what that actually is y equals negative x. This one, the domain would be negative infinity to infinity. And the range is going to be starting at 0, so 0 with a bracket, on upward to infinity. The last function we're going to look at today is what's called the greatest integer function. On a calculator, you would get that by going into the math menu, and one of the choices says int. So you want to put int x on your calculator if you're graphing it. Greatest integer, what it means is you take a number and you want to know what's the greatest integer less than or equal to that number. So if I had a number like a half, the greatest integer less than or equal to that would be 0. If I had a number like 3/4, the greatest integer less than or equal to that is 0. If I had 0, the greatest integer less than or equal to that is 0. And same thing with other numbers. If I had like 7.9, the greatest integer less than or equal to that is 7. If you had negative 4.1, you'd go down to negative 5. You're looking for the greatest integer that's less than or equal to something. Basically, it's like you're always taking a number and rounding down. Now, on my old cheap calculator that's built into the computer here, you get kind of an ugly graph. And it's not the most accurate portrayal of what the graph actually is. But what we do end up getting is like stair steps that go up as you go from left to right. Here's a somewhat more accurate portrayal of what it would look like. And again, you can see it does go up in stair steps. I have some numbers that round down to 0, some that round down to 1, some that round down to -2. The stair steps keep going to the number at the left. I put on here a notation that we often will use to talk about the greatest integer function that almost looks like absolute value. But if you look at the bottom of those bars, they have like little feet that point inward. This is also sometimes called the floor function because it's like if you have a number that's above the floor, you round it down to the floor. So it's like standing on the floor is almost where that notation comes from. And again, if you see these bars that have little horizontal marks at the bottom, that's going to be the floor function where you round the number down. Now, in this chapter, the number one thing you want to do is just recognize the shape of those different functions from their graphs. Know which one's which. But we're also going to figure out that you can take those functions and come up with other things from them. If you have a function that has an equation similar to one of those parents, the basic graph is going to be the same. You actually did that last year in trig class when we learned how to graph sine and cosine functions, and you figured out that you could change the numbers around and come up with things that were still sine and cosine, but maybe they were a little bit taller or shorter or fatter, or they moved up or down. You can change things depending on numbers that you put in with those functions. Depending on what you do, things might move to the left or right or up and down. They might be stretched because of numbers that you change. There will be a second video that goes into what some of those changes are, but our goal is to learn what happens and be able to make quick, rapid sketches and get an idea of what's going on with functions, which a lot of times is really quicker than trying to mess with it on a calculator or computer. So hopefully that gives you an idea of the main parent functions that we end up using in analysis.